Hello. We will now look at problem 3, spring 2018, week 5, which talks about diagonalization and eventually the relationship between diagonalization and invertibility of matrices. So let's start with the first part, which is 3A. And this talks about when A is an n by n matrix diagonalizable. So in other words, under what conditions. And under what conditions? So we know that for any matrix, given that it's n by n, we can solve the characteristic equation of its eigenvalues. And this gives us perhaps n distinct eigenvalues. Perhaps it gives us n eigenvalues where some of them are repeated. Once we do this, we can find eigenvectors. And it is both sufficient and necessary that if we have n eigenvectors, which are linearly independent, that we can diagonalize an n by n matrix as PDP inverse. Now, what is key to note is you need n eigenvectors which are linearly independent. You don't need n distinct eigenvalues. So the most common example of this is to talk about the identity matrix, right? If you think of the identity matrix, you can see right off the diagonal that its eigenvalues are all 1. However, the identity matrix is already in a diagonal form, and we see that all we need is n distinct eigenvectors. In this case, n is 3, and the 3 eigenvectors we can take are E1, E2, and E3. Note in particular, anything is an eigenvector for the identity matrix because Ix equals x for all x in the domain. OK, so that was part A. And now let's talk about part B. Part B asks us, given some eigenvalues, we wish to diagonalize a given matrix. So OK, let's start with the case of lambda equals 1. In that case, you have A minus lambda I is A minus I. And this matrix is 1, 1, negative 1, 0, 1, 0, 0, 1, 0. OK, and now what we need is any eigenvector corresponding to lambda equals 1 belongs to the null space of A minus I. So we're trying to solve the equation that this matrix times, so we'll get rid of this part. Is there any way to like cut and paste a matrix? Oh, screw it. So now, solving for the null space of A minus I, what we're looking to do is solve the set of equations given to us by this. OK. So right off the bat, notice that this column and this column are exactly identical. So at some point, we will have some redundancy. So the first equation gives us v1 equals 0. The next one gives us v1 plus v2 plus v3 equals 0. And the last one gives us negative v1 equals 0. Now, clearly both these equations, so this one and this one, are same. So really, we have one equation which says v1 is 0, and then another which says that the sum is 0. So in our hand, we have one free variable, so let's fix it. So let's say v2 is some t. Then it follows that v3 must be 0 minus t minus 0 equals negative t, where I get this from this equation up here. OK, so all of this lets us solve for one eigenvector. So the eigenvector corresponding to lambda equals 1 will be of the form 0, 1, negative 1, right? And if we like, we can normalize this to be 0, 1 by root 2, and negative 1 over root 2. OK. So now let's solve for lambda equals 2. In that case, we first compute A minus lambda I, which is A minus twice the identity. And we get 0, positive 1, negative 1, 0, 0, 0, and 0, 1, negative 1. Now notice, this is a column of all zeros, and these two columns are identical. So really, we will have two levels of redundancy in this system of equations. So let's say I am solving for the null space. So I want to solve the equation this times v1, v2, and v3 equals 0. So okay, the top row gives us absolutely nothing because you get 0 plus 0 plus 0 is equal to 0, and we gain no useful information. The next row gives us v1 plus v3 equals 0, and the third row gives us negative v1, negative v3 equals 0, but these two are identical. So this is just saying v1 equals negative v3. So first, we have absolutely no equation on v2, which means v2 can be whatever it likes. So let me fix it to be some t. And now we have only one equation between these two guys. So one of them needs to be fixed. So let me say v1 is some k. Then you have that any eigenvector of the matrix A corresponding to lambda equals 2 is an eigenvector. Then you have that any eigenvector corresponding to lambda equals 2 for the matrix A is in the null space of this matrix and is of the form k t negative k, where the k comes here, the t comes here, and the negative k comes from that equation there. Now, since t and k are independent, this is really a linear combination of two eigenvectors, which is 1, 0, 1 times k plus t times 0, 1, 0. And we can verify that both this, let's call this v sub 2, and let's call this x1 and x2 are linearly independent. And the easiest way to see it is because there is a 1 here and a 0 here, so there's no linear combination you can make. And finally, we can verify that these are both eigenvectors of the matrix A. So then we see that corresponding to lambda equals 1, we get the eigenvector v equals 0, negative 1, 1. And corresponding to lambda equals 2, we get the eigenvectors 1, 0, 1 and 0, 1, 0. And we can normalize everything as necessary. Now, when we go to diagonalize this matrix, we can see first and foremost that all three, wait, hold on. Yeah, okay, reset. So now when we go to diagonalize this matrix, we can see that clearly this eigenvector here and this one are linearly independent. Further, these two are linearly independent because there is an entire new column entry. And then these two are also linearly independent. And we can verify that all three are in fact linearly independent. And then we can diagonalize the matrix A as, let's just stack them up, 0, negative 1, 1, 1, 0, 1, 0, 1, 0. So this is the P matrix. Now corresponding to 0, negative 1, 1, I have the eigenvalue of 1. Corresponding to the other two, I have the eigenvalue of 2. And then this is my D matrix. And then finally, I have P inverse, which can be computed using P. So that was the diagonalization of this matrix A. OK, so let's start with part C, where we're given a transition matrix of a pump. And we don't know in particular what the pump system looks like, but all we know is that there is a transition matrix, which means the equation that the state vector at time n plus 1 will be the transition matrix times the state vector at time n. Well, if I go on to solve this recurrence, I get a squared times the state vector at time n minus 1, and I can keep continuing this to get a to the n times the state vector at time 0. All I really did is I said, well, s of n will be a times s of n minus 1, and then I can recursively solve this entire system, is a of s of n minus 2, and so on. Well, OK, if this is true, then really all I need is to find a to the n in terms of the eigenvectors and the decomposition. So this is going to be PDP inverse. This is 1a. And then PDP inverse, and then this is the other A, and then I keep going, and I get PDP inverse, and this is n times. Now what you can see is that these adjacent P inverses, and say there is another PDP inverse here, and then these guys, and then these guys, all cancel out to be the identity. So this simplifies out to be P times D, 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 P inverse. And how many times do we have D? Well, we'll have it once for each time it showed up. So n times. And then we conclude that A to the n is P D to the n P inverse. Let's take a moment to think why this is useful. Notice that D is of the form lambda 1 through lambda sub n. Let's use different notation. Let's say lambda sub k, and all zeros everywhere else. This implies D to the n is really just lambda 1 to the n dot 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 lambda k to the n, and all these guys stay 0. So then we really don't have to do matrix multiplication n times. All we have to do is take the powers of D, raise it to n. And this makes it computationally much, much, much more efficient. OK, so finally what you can conclude is S of n plus 1 is P D to the n P inverse times S of 0. For those of you who like a change of basis perspective on these things, what this is saying is we're converting into a different basis, often known as converting into the eigenbasis. You're multiplying D to the n in the eigenbasis, so you're rescaling. And finally, you're going back to the standard basis, which is exactly what we would have done if we had used the transition matrix A. All right, so now let's get started with part D, which asks us, on a fundamental level, is there a connection between invertibility and diagonalizability? And often intuitively one thinks, yes, if you're invertible, then there is some linear independence to your columns, and then you must be diagonalizable. But we'll see through this problem that really, for invertibility, what we have is that the columns of A need to be linearly independent. And for diagonalizability, we have that the eigenvectors of A need to be linearly independent. And we'll see through counterexamples that linear independence of one or the other does not guarantee linear independence of the corresponding other. OK, so first let's go the first way. So let's say A was invertible. Let's pick such a matrix. So let's take, say, this matrix, right? The simplest one we can think of, which is this guy. Now, this particular matrix, if you were to invert it, this actually just comes out to be, so we take the determinant, which is 1, and what is it, this?
No, it's, so the diagonal entries get exchanged, but the other ones get negated.
Oh, just negated as is, in place, OK.
Also, for the diagonalization, the eigenvectors are not necessarily just linearly independent, but there should also be enough of them, right?
There'll always be enough of them. You can superfluously add linear dependencies. So we have this matrix, and we want to take its inverse. So let's do the 2 by 2 matrix inversion formula, which gives us the 1 over the determinant, where the determinant is AD minus BC, so just 1. Now the diagonal entries stay exchanged, but 1 and 1 is still 1 and 1, and the off diagonals get negated, right? And one can go ahead and verify that, in fact, this is the inverse. So we have that for part 1, let this be my A matrix. Well, then this is an invertible matrix. But now we'll see in a minute that it is not diagonalizable. So let's solve for the characteristic polynomial. So let's solve for A minus lambda I, and its determinant being 0. So you get lambda minus 1 squared is 0, where what I did was I had 1 minus lambda, 0, 1, 1 minus lambda, and I took the determinant, and through the formula I get this. I set it equal to 0, at which point I conclude lambda equals 1. So the only eigenvalue I have for this matrix is 1. So Now let's solve for the null space. For lambda equals 1, A minus lambda times the identity comes out to be 0, 0, 0, 1. And let me say I'm solving for the null space. So I say, okay, well, A minus lambda I times V must be 0. So then this times some V1 and V2 must be 0. And you get V2 equals 0 from the first row. But from the second row, you get no new information because you get 0 plus 0 equals 0. So any eigenvector to this matrix will be of the form 1, 0. However, I only got one eigenvector, and any other eigenvector that I solve for must only be a linear combination of this guy. And then I conclude that I don't have enough linearly independent eigenvectors, and therefore A is not invertible. I have only one eigenvector, and therefore I must conclude that A is not diagonalizable. Okay, so that was part 1. Now let's look at part 2. So let's say we have a matrix which is diagonalizable, right? So let's take the simplest thing I can think of, which is 1, 0, 0, 0. Notice this matrix is already in a diagonal form because you have entries only along the diagonal and zeros off the diagonal. Okay, so A is diagonalizable and it's given in the diagonal form. And then I need to ask, is A invertible? And there are two ways to see this. You can solve for the determinant of A, which we see comes out to be 0. And then you conclude that if your determinant is 0, you are not invertible. On the other hand, you can also see that the second column, which is 0, 0, is 0 times the first column. And so the calls of A are linearly dependent. And so we see that at a fundamental level, there is no connection between invertibility and diagonalizability. One relies on the linear independence of eigenvectors, and the other relies on linear independence of the columns of a matrix. Thank you.